This is Suvarchala working as an associate professor at the Institute of Aeronautical Engineering. As a part of the design and analysis of algorithms lecture series, in this video I'll explain how merge sort works and in which situations merge sort is more beneficial to us. So this video includes procedure of merge sort, algorithm, some examples and analysis of merge sort, and also we will discuss how for various applications this merge sort can be used. Various sorting techniques we discussed already. Insertion sort, incremental approach, it sorts in place, order of theta of n is the best case, worst case is theta of n square. Similarly, bubble sort is also incremental approach and in place sorting and theta of n square running time. Selection sort also incremental, in place sorting only theta of n square, whereas merge sort is following divide and conquer strategy. And is it in place? No, but we will see it, and also running time also we will discuss further. As we know that divide and conquer strategy divides our problem into number of subproblems similar to the subproblems of smaller size and conquer the subproblems and then combine the solutions of these subproblems. Conquering of subproblems is going to be done through recursion process actually. So, by using combining solutions of these subproblems, the solution for the original problem can be obtained. Merge sort is based upon this divide and conquer approach only, or divide and conquer strategy only. So, merge sort means here the term itself indicates merge. Merging operation is going to be included in this merge sort technique actually. To sort an array of elements, we have to divide our array of elements into two halves, two subsequences, in other words, two sub-arrays, and sort the subsequences recursively until we will get each subsequence contains a single element. Then combine the results by using merging of the subsequences. That is, combining concept is here merge the results of these subsequences from bottom to upward direction. So, every time we are dividing, so that this concept is going to be continued division to conquer the results of each subsequence having only a single element actually. So, this is going to be represented a overall procedure. Merge sort array, P are the lower bound and upper bound of the array. If P is less than R, remember, if P is less than R means lower bound is less than upper bound. If it is greater than or equal to, what happens? Our array size. Greater than means array is exhausted. Equal to means array consists of a single element. So P equal to R means lower bound equal to upper bound means array consists of a single element. It is already in sorted order single element. So no need to consider further actually. So that's why if array consists of more than one element only, this merge sort process is applicable. What we are doing, the main concept is divide your array into two sub-arrays. Right? Again, apply the same process, two sub-arrays, and so on and so forth. Each sub-array consists of a single element. So that's why we are considering Q. How to divide? Q is going to be floor of P plus R by 2. We can take either upper value or lower value, but the same must be considered throughout our program. So, middle value we are considering 1 to, that means lower bound to middle value is first subsequence, middle value plus 1 to upper bound is second subsequence. So, again we are applying merge sort recursively for the first half and for the second half. Again, we are using this merge operation. How it works we will see. By using this, initial merge call will be for A is equal, lower bound is 1, upper bound is n, or in some languages lower bound is 0, upper bound is n minus 1. So if you observe here 5, 2, 4, 7, 1, 3, 2, 6, P is 1 and R is 8. 8 plus 1 by 2 is 4.5. Floor value you have to consider. So 4. Right? So 4 means Q is our 4 now. We are dividing our entire list into 2 sublists. What is the first sublist consists of? 5, 2, 4, 7 up to Q. That is P to Q. Second sublist is Q plus 1. Q plus 1 means fifth element onwards. That is 1, 3, 2, 6 up to upper bound. Second sublist. Like this division process is continued and we will conquer the results. So divide, conquer, then combined. This is the base. Every time we have to check the base case. If the sublist consists of a single element or exhausted, then you can stop the process actually. So this is the way it will work. Just diagrammatically would like to show you. So first initial values of our list are 1, 2, 5, 2, 4, 7, 1, 3, 2, 6. 2 sublist you observe. 5, 2, 4, 7 is first. 1, 3, 2, 6 is 7. Because Q is 4 in the first initial stage. We are not, just we are dividing and we are placing there only initially, please remember. Right? So again, 4 elements are again more elements. Our lower bound is up, less than upper bound. It is further divided into 2 elements. 5, 2, 4, 7. Again, 5, 2 is divided because you observe darken is going to be considered as the middle element in this case. So 5 will be in 1 and 2 will be in other. This is division of our array into 2 halves recursively. So like this we got. How many sublists we got? 1, 2, 3, 8 elements are there means 8 sublists will be there. Now further division is not possible because in each of the sublist is going to be having element. Our lower bound is equal to the upper bound. So that's why it's not further possible. This is the process of division process, dividing process. Conquering, divide and conquering process actually. Combining the results. We have to merge the results or combine the results. How to do this? So this is divide process. Conquer and merge. So conquer and merge means this division is happened. What is our current status? The last one is the current status. Conquering and combining the results will be from last to upward direction. Original result we have to get in sorted order. So that's why you observe. Now the process is towards this direction. Bottom to up. What we have to do? 2 consecutive subsequences must be merged. Conquer and merge. So conquer means each of these sublist is already in sorted order. So combine the results because 5 is sorted order. 2 is sorted order. Because 1 element means it is sorted only, no? So that's why. So we are going to merge these values here by 2 consecutive sublists. So that means these 2 are merged, these 2 are merged, these 2 are merged, these 2 are merged. So while merging, what is merging? Merging is combining the 2 sublists. Prerequisite of merging means 2 sublists must be in a sorted order. While merging, after merging, we will get the merged list again in the sorted order. That is the basic merging process actually. So we'll discuss one more example with the detailed process of the merging. Now currently just we are showing you how this is going to be processed internally. So here 2, 5, 5, 2 is there, no? After merging sorted order, we will get 4, 7 sorted order, 1, 3 sorted order, 2, 6 is sorted order. This is the first level. Then what happens again? Consecutive 2 sublists must be merged. That means these 2 must be merged, these 2 must be merged. 2, 4, 5, 7. 2, 4, 2, 5, 5, 7. 2, 5 is in sorted order, 4, 7 is sorted order, input list. After merging, we will get, how to get? 2, 4, 5, 7. Sorted order will be considered, merging. After merging, the result will be in sorted order. How it will be resulted? I'll explain after discussing the algorithm. Similarly, these 2 sublists. Now, these 2 sublists are again merged so that I'll get the original list. What is the original list? The original list is in the sorted order actually. So, this is the divide and conquer process. So, that means we have to represent our elements 2 power of n. we able to represent our elements as 2 power of n, some n value. If it is not sufficient, empty locations can be considered by us. So this is the merge sort algorithm, our notational wise, algorithmic notations which we discussed in earlier videos. Based upon that, this is the algorithmic notations wise, this is a merge sort algorithm. So A, low to high is a global array. If low is less than high, that only we consider P, R, and mid is Q. Here in other example, Q considered mid value, low plus high by 2. And merge sort we are going to call again back low to mid and mid plus 1 to high. And combine the result. Sort one subset, sort another subset, combine the result. Combining the results will happen after completion of this division process. Please remember, this is going to be recursion, no sorting process is going to be done, or merging process is going to be done after completion of the division actually. So this is the algorithm, this is the overall algorithm of the merge sort actually. But what is the another algorithm used here? Which algorithm? Merge algorithm. So how this merge algorithm is working, we are calling no. So first we have to learn how it works. Merging of two arrays we are considering. Two arrays means here, but these, remember how these values are stored. Same array the values are available. Only two arrays means we are having the lower bound and upper bound values of the two arrays. You observe, 1 is lower bound and 4 is upper bound of this sub-array. 5 is lower bound and 8 is upper bound. Same array elements only, but we are considering them as a 2 halves, 2 halves, 2 halves, just by stating their lower bound and upper bound value of the subscripts actually. So that's why array is A only here, and low, high and mid. Low to mid is the first sub-array and mid plus 1 to high is the second sub-array, which have to be merged by us. Clear? And for merging, we need some auxiliary storage or additional array. We will consider this additional array as a B here. We need an additional space for that. So B array we are going to use while merging. Temporarily we would like to store our results. So that's why B is used. So we will consider here, that means by after merging our first sub-array and second sub-array, the merged results are going to be stored in third sub-array, a new array. For this purpose only this auxiliary space, additional space is required as a workspace for merging process actually. So that's why we are going to have H is going to be low, we are assigning H is representing low and I is also representing low, J is representing mid plus 1. Right? So we will consider here, we are starting from the lower bound. While H is less than mid and J is less than high, then onwards J is less than high means second half. So J, from J to high is second half. From H to low is first half, or you can say H to I is first half. And this I value we are going to consider as low because I represents, it is going to be stored in the additional elements, no? So B is used. In that B, the data will be stored from ith location to the again high value. Understand? So for that purpose only this I is used. So while H is less than mid and J is less than high means as long as the two sublists are not exhausted, we are checking H is moving towards equal to mid work means it is first sublist. J is equal to high means second sublist. So we are checking both are not exhausted. Both are not exhausted. If one of them got exhausted, it will come out of the loop. Then what happens we will see. We are checking every time the first element or H element of Jth element comparison, whichever is lesser value, that is written in the new array B and respective indices are incremented. That means H is less than A of Ij means A of H is going to be written in the Bth array. So that's why B of I is equal to A of H and H will be incremented because it has been written in the resultant word. No? So that's why it is incremented. Otherwise, and A of j element is going to be written in B array and j will be incremented. In either of these two cases, I will be incremented. Why? Because we have written some value to the new array. New array index has to be incremented. Similarly, the remaining elements of the first sublist is going to be copied, or the remaining elements of the second sublist are copied, depending upon the condition satisfied either of these two. If h is greater than mid means it will works, it will h to mid, remaining elements are going to be written. If j is greater than high means second sublist exhausted, first sublist values are going to be written here. That means after merging, all elements are stored in the array B from ith position to I plus 1 high position. So again, these things must be again copied back to my original array so that it will be in sorted order of the original array only. This is the merge process we considered actually. Right? So if you are going to select 8 entries here, division is going to be happening like this, half, half, half like that. And 7 to 7, 2 to 2 means single elements are there. Merging starts here back. And the respective indices are like this actually. First array is 1 to 8, second array is 1 to 4 and 5 to 8. And 1, 2, 3, 4. All these are indices. That means we are using same array till this process is division is continued. While merging only for working, additional space is used. So these are the indices of the sequence of recursive calls of our merge sort algorithm having 8 elements actually. Right? So we are going to consider after processing pre-representation of calls of the processes of merge, it will start from the lower to upper, So the indices are going to be 1, 1, 2, 3, 3, 4. That means these two are merged. You will get 1, 2, 4 and 3 is going to be considered. And the respective things are going to be 5, 6, 8 will be considered. Further, the process is considered. That means these are the indices while merging. These are the indices while merging actually. Right? So like this, these indices are going to be used in the same array so that what happens, the values are available after sorting also. Original data will be considered in the array, array A. Again, after sorting also, the elements will be in the array A only. But we will use only B while processing the merge as an auxiliary storage or a temporary storage actually. How it works, we will see further. So this is the given list. Divide into sublist. This is the division is continued. Each sublist has one element now. Now, the recursion process is going to be starts working in upward direction merge process. As I explained to you earlier, merge sublist to make the sorted list. At the end, we will get the sorted list in the same array. In the previous slides, I explained how the respective indices are going to be considered. Now, this is the way we are going to represent the data actually. How the main logic you understand for division process. Mid value from mid to low to mid, mid plus 1 to high. Like that, this division is carried out till we get each element is considered as a subsequence. But merge, how it works, we will see through some example. Right? So let us assume that 2, 4, 5, 7, 1, 2, 3, 6 are there. P, Q, R are there. Array is given. One single sorted subarray is there. Unsorted subarray. We have to get sorted subarray. So let us assume that if you would like to merge two sorted cards, choose the smallest one. For example, two sets of cards are there. Already those are in sorted order. How it will do? Choose the smallest one of the top two cards and remove it and place in the output file. Repeat the same process until the entire pile is empty. That is either first pile or second pile. Right? So take the remaining input of the piles, which is leftover cards are there. Those are going to be face down onto the output file. The same logic we will consider. For example, 2 piles of cards are there. We will see topmost one sorted order now. Whichever is lesser one, that will be put in the output. And again, we will compare the topmost again. We removed one now. So that's why again topmost of these 2 piles. Same process is continued until any one of the piles is get emptied. The remaining elements of the any pile leftover elements of the pile are going to be copied as it is actually. So we'll take some pointers and I'll explain P, Q, R. 8 to 17 are there. Let us assume that. So that means our P is 9 and Q is 12. This is for first sublist 9 to 12. 9 to 12 means what are the values? 2, 4, 5, 7. And 12 means 13. Q plus 1 no. So 13 to 16. 13 to 16 means 1, 2, 3, 6. These are the 2 sublists we are having. So left sublist is having 1, 2, 3, 4 infinity. That is 2, 4, 5, 7 is first sublist. And second sublist is 1, 2, 3, 6 we are having as per our PQR. Original sublists are already in sorted order. How to merge? Let us assume that this is left sublist. This is R sublist. Left sublist into 6 is I. R sublist is J. And we are generating how to. I'll compare first these 2. First elements 1 and 2. 1 is lesser, so 1 is copied. Okay, 1 is copied means next element is 2 in the second sublist. Again 2 and 2 are considered. And the respective 2 is going to be added. This process is continued. That means here you observe I, J. When we are considering 2 and 1, 1 is lesser value, 1 is going to be written in the output, no? So that's why that is going to be crossed. What are the remaining elements? 2, 3, 6 here. So I have to compare with I value is 2, jth value is 2. We are going to compare I value, jth value and leftmost value 2 is there. I am going to copy that one into the original list 2 and crossed. Now I index is second element. Second element means 4 and 4 and 2 are compared. 2 is lesser value. That is copied into outer one. So 2 is striked off in the sublist. And after that, ith value is 4 and jth value is 3. These 2 are compared. 3 is going to be copied. So that's why 3. Next, 3 is going to be striked off. You observe here. Next, 6 is compared with 4. 4 is lesser value. 4 is copied into out. So that's why 4 is going to be striked off here. What are the elements are left over in the left sublist? 5, 7. Here 6. Now we are going to compare ith value is 5 and jth value is 6. These 2 are compared. 5 is lesser value. So 5 is going to be written into my original sublist. And temporary sublist or original sublist. These are going to be stored here. So what are the leftovers here? 7 and 6. 6 is lesser. 6 is going to be written into our sublist and original sublist, rewriting original sublist, and 7 is left over. By this time what happens? The right sublist is going to be got exhausted. It will come out of the while loop. So which elements are left over? Some elements of the left sublist are left over. Those are written copied as it is from ith position to end of position. Only one element in this example that is going to be written directly. Now you observe the merging is after merging. To merge this, these sublists are written in the some additional array. Or we can use this additional array or original place, write this sorted data into some other list and copy them. Either of them are okay for us. So this is another example. We are using some PTR pointer. So H pointer, J pointer, K pointer based upon our original algorithm was explained to you. Now you observe here in the first table what are the values are there? 1, 13, 24, 26, 2, 15, 27, 28. Indices are 1, 2, 3, 4, 5, 6, 7, 8. This is the 1, 2, 3, 4, 5, 6, 7, 8 are the original data. That is the temporary data I am using. We will compare H element, Jth element. H element is 1, Jth element is 2. While comparing them, whichever is lesser, 1 is lesser, that is copied into my new list. Once copied, this must be incremented. H must be incremented. So now H points to this. I points to the next element. I pointer points because it has been written, no, it will be pointed. Now comparison again H and J. H value is, H means the respective index value is 13. Jth index value is 2. So comparing 2 is going to be written here. Now J will be get incremented. That means you understand whichever the element we are writing, copying from the sublist, the respective sublist pointer is going to be incremented. Now you observe jth element is incremented 15. 15, 13 compared. 13 is lesser value. So 13 is copied. 13 is H increment value, no? So that's why H index value, no? The H pointer is incremented to the next one. That is H is pointing to 24 and J is still pointing to 15. Now when we compare these 24 and 15, 15 is lesser, 15 is copied, then J is going to be incremented. That Jth value is going to be 27. Next 24. So 24 is jth value and H value is, jth value is 27, H value is 24, lesser value is H. So that's why H is copied, H is incremented, 24 is copied. Now H points to 26, J points to 27. Then what happens here again while comparing 26 and 27? 26 is lesser value, 26 is written and J got exhausted, H got exhausted. What are the elements are left over? So this is, first part is not at all. Because lower bound is, our H pointer is crossing our upper bound of this first sublist, we will stop that part. But the remaining elements, which elements are left over? Our J is not still less than the high value. So that's why J elements are copied as it is. 27 is going to be copied. Then J is incremented. 27 is copied. Then J is incremented. 28 is going to be copied. Then the sorting, merging of the process is continued. That means this merge process means we supposed to remember to merge two sets of values or two sequences of values. Basically, these two sequences must be already in sorted order. Then only we will get after merging in a sorted order. While at which level merging starts, the level at which each sublist is having a single element. That means those are already in sorted order. From there onwards, it will work in towards the upward direction to get our original sublist. So how much time it will take and how much space it will take? What is the analysis or efficiency of our merge sort algorithm? So which one is more considerable process here? The main logic is involved in the merge. But even though it is merge is there, the merge algorithm takes only linear time only. Because initialization and copying of two elements, no? So that's why temporary arrays we are using only to the n iterations will be there every time. Outer loop or inner loop, whatever it will be considering. You are considering only a single loop in algorithms, not a nesting of loops. So it will take linear array only. So the total time for our merge will be some 3n or 4n, whatever it may be. But order of theta of n will be the total time of the merge process. Total time taken for the merge actually. But total sorting is going to be depends upon the recurring process. No, so recursion we have to consider. So the recurrence is based on these recurrence algorithms, how to generate a recurrence relation from the recurrence process of divide and conquer algorithm can be represented. T of n is the running time of the problem size n. Divide the problem into a subproblems. No, that's why a of t of n will be there. But each of the subproblem is having a size n by b. Then it will be considered as each subproblem is going to be taken a time a of t of n by b time. We have to compute size of the subarrays. But a subarrays are there, no? So that's why a into t of n by b. And every time we have to consider merge process, no? D of n is going to be, this division process is taken a constant time d of n. And C of n is taken as a merging process time actually. If T of n is equal to 1 means the time complexity is 1 itself, because we are going to divide our merging process, merge sort technique, divide our sublist till each of the size 1. Each of the size 1 means how much time it will take? It will take only 1 constant time. Because a single element is already in sorted order, no, it's a constant time. By using this, that means our merge sorting is going to be A T of n by B plus division complexity plus combining complexity. This is the generalized divide and conquer algorithm recurrence relation. In our example, our B value is 2. By 2 we are doing actually 2 sublist we are getting. Our A is also 2 actually. A, B values are 2 in our merging process actually. So that's why dividing constant time. Conquering means recursively solve 2 subproblems every time. As I told you, half of the size. So n by 2 is the size and 2 subproblems no. So that's why 2T of n by 2 is our conquering recurrence relation. And combining is a merging process. Already we discussed merging process is theta of n. Linear time it will take. So what is our recurrence relation for merge sort technique is T of n is equal to theta of n if n is equal to 1, that is constant time. Otherwise, if n is not equal to 1, then 2t of n by 2 plus theta of n. This is for 2 sublist sorting recursively, and this is for merging process for n greater than 1. This is the recurrence relation. We can solve this recurrence relation by using either Master's theorem or substitution method. If it is a Master's theorem, we will compare the values of n with f of n as a Cn. Cn is the combining of the results. So T of n is equal to theta n log n by substituting the value of A to 2 as well as B to as B2 as for B value. We will get the time complexity of this algorithm is n log n. But we can use our any of the substitution method also. For n is equal to 1, the time to merge sort is constant, which will be denoted by constant time, and we represented n as the linear time as respective positions actually. By using this recurrence relation or through some specific concepts we can use, or we can use the respective substitution method also. So already Master's theorem, we applied directly applying Master's theorem, we will get n log n only. But by using substitution method, T of n is equal to T of n by 2 by n by 2, we are going to T of n by 2 plus 1 we are going to get. So n power is going to be considered here. So we keeping on substituting the values, we will get 1. That is n by 2 we are substituting. In n by 2 again, n by 2 you substituted, that is n by 4. Again n by 4 means T of n by 4 means again n by 4 by 2 no, n by 8. So this process is continued till your n value becomes as a 1 actually. So 1 means our n is also 1, this is also 1 where T of 1 is 1 you are getting, and we will get T of n by n as a T of 1 by 1, which is equal to logarithmic value log n will be there, or n log n will be considered. So 2 power n we will obtain. So that's why based upon that n log n we will get actually, as we discussed already in the recurrence relation video. So T of n is equal to n plus n log n. N is for combining and n log n is for our merge sort recurrence relation solution. So we will get the time complexity of merge sort is order of big O of n log n, and this is for all 3 cases: worst case, best case, and average case. With reference to merge sort, all 3 are going to be equivalent, because in the merge sort based upon the arrangement of the data, this is not going to be changed. In any case, all these are divided into single sublist and sorts data through merging process by merging sublist, no? So that's why irrespective of the respective arrangement of the original input, that means worst case, average case, and best case, the time complexity of merge sort is n log n only. Of course, depending upon the size of the n, some space complexity can be considerable by us. So we'll discuss some problems related to sorting. Which sorting method is most suitable to such problems? For example, one problem I'll consider: sort a file of huge records with tiny keys. Key length is very less, but the record size is more actually. For example, recognize our MP3 files. In our MP3 files, size of the file is going to be considered as very, very huge, but the name of or identifier of the file is going to be very small key. Then which sorting technique is more suitable? Merge sort, guaranteed to runtime as a n log n approximately, selection sort, bubble sort, or a custom algorithm for use records with tiny keys. Custom algorithm means we have to generate our own algorithms, or insertion sort. Which one is better one actually? First we'll consider insertion sort or bubble sort. Because insertion sort and bubble sort are based upon incremental as well as having the same complexity. It is not possible because too many exchanges are required. So that's why high data must be interchangeable. Because record size is more now, so it will take more time. Selection sort, yes, it may take because it takes linear time for the exchanges. Selection sort may be suitable for such data sorting actually. Merge sort, probably not. Why? Because selection sort is simpler comparing with merge sort. Because our selection sort takes less swappings comparing this merging process. Because it has to divide into sublist, sublist, sublist. Again, we have to merge back now. So it may take more time comparing with this selection process actually. We'll consider one more example. A problem: sort use randomly ordered file of small records. Record size is less, but more number of records are there. These things are happening in most of our real-time applications. For example, process transaction record for a phone company. So for a phone company means use calls we are going to do, but each call and time etc. record size is going to be a smaller record size. Then which sorting method is there? Bubble sort, selection sort, merge sort guaranteed with runtime, or insertion sort? Selection sort is no, because always it takes quadratic time. Even bubble sort is also quadratic time. Insertion sort is also quadratic time for randomly ordered queues. So merge sort is n log n. Comparing with quadratic time, it takes lesser time. So merge sort is going to be used to design these problems actually. That means depending upon the problem, depending upon the size of the input, and depending upon the record size also, even though we are not considering directly record size also, we have to select a particular sorting techniques to sort our data. For example, another problem we'll consider: sort a file that is already almost in order. So sort a file that is already almost in order means we discussed in previous video about quicksort also. That will come as a worst case in quicksort, but not in merge sort as I told you. So that means resort a huge database after a few changes is one of the examples. Double check that someone else sorted the file or not. In these two are the applications in which the data is already in sorted order, but we need to apply sorting again. Which technique is more suitable? Merge, selection, bubble, custom algorithm, or our insertion? Selection, quadratic time, and bubble sort is also quadratic time because already in sorted order. So for example, it is A, B, D, E, F, etc. If you are taking, even though it is sorted order, it will take quadratic time only. Insertion sort, yes, because linear time for the most of the definitions almost in place now. So that's why when we are searching for its place, it is in its place only. So it's not a linear time sometimes. Probably merge sort or a custom method. Insertion sort simpler or faster than our merge sort in this example, because your insertion sort takes linear time as best case here. So that's why. So comparison of these sorting techniques which we discussed up to certain sorting techniques we discussed, based upon which bubble sort, selection, insertion, quick and merge, and heap sort, if you are going to consider the best case, average case, and worst cases. If we make it as a table so that for further comparison it is very useful. But merge sort, if you don't know the data size or a data, how the data was arranged, etc., in such cases, better go for merge sort, because in all cases it will be n log n only. But coming to this space complexity, we'll discuss further space complexity. We will based upon whether the particular sorting algorithm is in place or not. What is in place sorting, we'll discuss. Space complexity means here, for our bubble sort, selection sort, insertion sort will be having the same. Of course, quick sort is also some, up to certain extent, not much more space is required, constant type only. But for merge, we need more actually. Because while merging, we have to store the data in a temporary storage. Either sublist must be stored or resultant of the merging must be stored temporarily in a new sublist. So that's why we, in such cases, we need some almost big O of n additional space is required. So how to check additional space is required means, if it is not in place algorithm, then additional space is required. That means, what is meant by in place algorithm? If an algorithm sorts our data without using any additional space and stores the result also in our input itself, input array itself, then we can say it is a in place algorithm, in place sorting techniques. I may consider some locations, 3-4 locations, constant number of memory spaces can be used for swapping or etc. But we need not, depending on, for example, n is my size of array. Again, additional n space is not required approximately. That means additional space is not required. The data of input is going to be stored in array A, and sorting is also done within that particular area only. So no additional space is used, no outside array is used to store our resultant temporarily or permanently. Then we can say our sorting is in place sorting. In case of in place sorting, no additional space is required. Understand? But merge sort is not going to be in place because it is using additional memory space while merging process. So that's why it is not in place sorting techniques. It needs additional space. So space complexity is more in worst case. One more characteristic also we will consider for sorting techniques, which we will call it as a stable sorting. So what is a stable sorting? A sorting technique is a stable if it does not change the order of the elements with the same value. So if the same value, so elements are there, after sorting also we will get as a group only. But in which order in the input is there, in the same order in output also it appears, then we will call it as a stable sorting. Generally, it preserves the original order of the input set, and while comparison also, it doesn't distinguish between the items, but the placing is going to be done according to their order only. That is, the stable sort will guarantee that the original order of the data having the same rank is preserved in the output. Same rank, same value order is going to be preserved in the output. That can be guaranteed if any sorting technique is stable. But remember, this stable sorting, merge sort is a stable sort. We won't interchange the values in merge sort. If you observe, just we are comparing and we are placing them. So whichever the order it comes, in the same order the data will be stored. For example, you observe here 3 dash and 3 double dash. Let us assume that. After sorting also, if you get like this, all threes comes as a group, no, but first 3 must be this one, second 3 must be this one, third 3 must be this one. Positional wise it will come. That is, the order is going to be retained. Such sorting technique is known as a stable sorting. 5 also, 5 and 5 dash. After sorting also, we are supposed to get 5 and 5 dash. But if you are getting like this 3 dash, 3 double dash, in such cases, we will call it as a unstable sorting. Most of the interchanges or swappings are there in algorithms. There, this stability can be get disturbed. You observe here also some color 10, 20, 20, 30 is there. While writing, this 20 will be first written, this 20 will be second outputted. Then we can say it is a stable sorting. So various sorting techniques, comparisons are replacement, swappings are there. There it is not a considered as a stable sorting. Bubble sort, stable, yes. Selection sort, no. Insertion sort, yes. Quick sort, no. And because it is interchanging, pivot element is placing, no. In such cases, some changes may occur. Merge sort, yes, because it requires an extra array to merge the sorted subarrays. So original order is not going to be missed. Coming to the in-place characteristic also, all are in place except merge, you observe. So for merge sorting technique only additional space is required actually. So based upon these characteristics, we will use our merge sort techniques for our applications. So what are the merge sort? Merge sort is useful sorting the data which is stored in the form of linked list. Even it is linked list, merge sort is applicable. Need not be array representation. Even linked list representation data is also there. Merge sort is very much useful in such cases. Merge sort is stable sort. That means it retains the elements of the order of the elements of having the same value in the output also. And overall time complexity of merge sort is order of n log n for all three possible cases. And it is more efficient even though worst case scenario occurs. Runtime is order of n log n. But only disadvantage is space complexity is order of n. Additional space is required. So running time insensitive of the input. So that's why time complexity, if you are going to consider the input size or the order of the arrangement of the input, doesn't affect the time complexity of the merge sort. Because all three cases it is same actually. But the main advantage is it guarantees always the time complexity is order of n log n or theta of n log n. Disadvantage is requires more space. These two are the more important characteristics of merge sort. Guarantees runtime complexity of always order of n log n, depending on it, irrespective of your order of the input data you are providing. And the disadvantage is additional space is required for merge sort, for the merging process actually. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.